Right now, beneath every healthy forest on Earth, trees are sending chemical signals to each other, sharing nutrients, and warning their neighbors about insect attacks, and they are doing it through a network of fungal threads so dense that a single teaspoon of forest soil can contain several miles of fungal filaments. This underground communication system, which scientists have nicknamed the Wood Wide Web, connects the roots of trees to a network of mycorrhizal fungi that acts simultaneously as an information highway and a nutrient exchange. Mother trees, the oldest, largest trees in a forest, have been documented preferentially sending sugars to their own offspring, recognizing their own genetic relatives in the dark beneath the soil. This is not metaphor. This is documented, peer-reviewed science. The assumption most people carry about plants is that they are passive, stationary, silent, mindless organisms that grow, photosynthesize, and die without any form of agency or communication. This idea is so intuitive that we barely question it. Animals communicate, we assume, because they have nervous systems, brains, and evolutionary incentives to share information. Plants lack all of these things. How could something without a brain, without a nervous system, without any apparent mechanism for cognition, be communicating information across distances about something as specific as which species of insect is attacking and how nearby trees should respond? The answer is that plants do not need brains for this function. They outsourced their nervous system to fungi 450 million years ago. The mechanism works through a symbiosis that evolved when the first plants colonized land. Mycorrhizal fungi are not parasites, they are partners. The fungi cannot photosynthesize, so they need the sugars that trees produce from sunlight. In exchange, fungi dramatically extend a tree's root reach, delivering phosphorus, nitrogen, and water from soil zones the roots cannot reach alone. But the network does something beyond simple nutrient trade. When one tree is attacked by caterpillars or aphids, its roots release chemical signals into the fungal network. Adjacent trees, receiving these signals through their own root connections, begin producing defensive chemicals, sometimes the same terpenes and tannins that make leaves unpalatable to the attacking insect, before they have been attacked themselves. The forest is executing a coordinated immune response. The research of ecologist Suzanne Simard at the University of British Columbia transformed scientific understanding of forests when she demonstrated in 1997 that Douglas fir trees transfer carbon to each other through mycorrhizal networks. Her later work showed that when a mother tree is dying, it floods the network with carbon and defensive signals, essentially a death bequest to the surrounding forest. Paper birch and Douglas fir, which compete above ground for sunlight, cooperate below ground by sharing carbon, birch shading fir seedlings in summer but supporting them with carbon through the network when the fir dominates in winter. The forest is not a collection of individual competitors. It is a single distributed organism with individual agents maintaining collective infrastructure. The implications extend to how we think about forest management and logging. Industrial forestry that removes old-growth trees, the mother trees with the most fungal connections, severs the communication network and leaves remaining trees isolated, vulnerable, and deprived of nutrients they had been receiving through the network for decades or centuries. Research on clearcuts shows that replanted forests grow significantly more slowly and suffer higher mortality when the fungal network is disrupted. Some ecologists now argue that sustainable forestry requires maintaining network hubs the same way telecommunications requires maintaining server hubs. Cutting too many connected trees crashes the network's function before individual tree health becomes visibly affected. There are documented cases of trees sustaining stumps, trees that have been cut down for years or even decades through the network by pumping sugars to the stump's roots. Stumps cannot photosynthesize. They have no leaves. They are technically dead above ground. Yet the network feeds them as if they are still alive, suggesting that surrounding trees either cannot detect the stump as non-functional or actively choose to maintain the connection anyway. In New Zealand, a kauri stump over a meter wide has been found alive, its cells still hydrated and metabolically active, sustained entirely by carbon from neighboring trees through fungal bridges. These stumps suggest something that plant neuroscience is only beginning to grapple with, that the networked forest may maintain connections even when immediate utility is unclear. When you walk through a forest now, you are walking through a conversation. Every step you take over roots and soil is a step over a communication network more ancient than the dinosaurs, more extensive than the internet, and more complex than anything we have yet fully mapped. Trees are not just trees. They are nodes in a distributed intelligence system that has been optimizing itself for 400 million years. The forest that appears still and silent is actually a place of constant signal exchange, resource negotiation, and mutual support. The next time you stand among old trees, consider, beneath your feet, the largest organism you have ever been near may be sending and receiving thousands of chemical messages per hour, managing the health of an ecosystem you cannot see, in a language that took scientists until the 20th century to even know existed.